Good morning, everyone. I appreciate everyone coming early and arriving. I hope everyone got a big breakfast. If you need seconds, go and get it. I want to thank everyone on the Liberty team for making these events possible. I'm sure, as most everyone here knows, we do a quarterly Liberty, human liberty, and energy breakfast. I'm usually just the introducer, but sorry for everyone that today you're going to be subjected to me for a much longer time. So I'm going to talk about a book that I wrote this winter, really mostly November and December, a ton of help with publishing, graphics, and editing from the Liberty team. Ryan Zorn, a new member of the Liberty family, has been a partner with me on the data, ideas, and some of the case studies in this. What I'll say up front, what this is not is a polemic or a policy proposal. We should do these 10 policies and get rid of those. To me, that should be done socially and in the political process. This is just the data. This is just the background and context that I think gives people a reasonable background in what the inevitable trade-offs are, and then decide the trade-off you want to make going forward. I'm going to go fast. There's a lot of data, a lot of slides, but we'll have a ton of time for questions at the end. So the very short summary of this book is, look, the last 1 to 2 centuries have just seen tremendous progress in the human living condition. I'll hit a little bit about that. I think 2 main catalysts: the growth of human liberty, bottom-up social organization, and the explosion in available energy because of hydrocarbons. The shale revolution, more recently, has turbocharged the energy industry. It's transformed energy markets, energy security, geopolitics. At the same time as this progress in the human condition, we have rising opposition to hydrocarbons. This is not in the developing world, but this is among the well-off in the well-off countries, but it's politically meaningful and impactful. So again, this book is to provide that data, that context for making decisions or forming ideas in this. Energy is the agent of change. Agriculture. 80% of Americans worked in agriculture 200 years ago. Today, it's 1.7% of Americans work in agriculture, 50% more calories per person than we had just 100 years ago, and we're the largest exporter in the world. You know, what's the difference? One word: hydrocarbons. Medicine. Medicine's as old as culture. But there wasn't a lot we could do for most all human conditions until recently. And if you look at that picture on the right, modern medicine, everything you see is a hydrocarbon. The equipment, the paint, the gowns, the masks, the techniques that they know and they can use to help save your life, all of that only came about because of the changes brought by hydrocarbons. All right, I wrote down 10 takeaways at the end, right before we publish this report. They are not marketing. They are not thoughtfully crafted to bring you in. They're just trying to summarize the facts. Energy is essential to life, and the world needs more of it. The modern world today is powered by and made of hydrocarbons. Hydrocarbons are essential to improving the wealth, health, and life opportunities of the other 7 billion people that want to be like us. They want to live the highly energized lifestyle of the lucky 1 billion. Hydrocarbons supply more than 80% of global energy and just countless materials, not meaningfully different than when I was born. The American shale revolution, I hit this one already, just transformed energy markets, energy security, and geopolitics. Global demand for oil, natural gas, and coal are all at record levels and rising. No energy transition has yet begun. Modern alternatives like solar and wind work in one sector, the electricity sector, and they don't even have prospects to replace most of the uses of hydrocarbons. Making energy more expensive, and we'll talk about case studies here, and unreliable compromises people, national security, and the environment. Climate change is a global challenge. I've worked in it for 20 years, but it's far from the world's greatest threat to human life. We'll go into that in some detail. Zero energy poverty by 2050 is a superior goal to net zero emissions 2050. In summary, for 2 reasons. Number 1, it's achievable, and number 2, progress towards that goal makes the world a better place. I can't say either one as true for net zero 2050. I'm going to be subtle, as you can tell. This is a plot on the bottom. This is the global energy system, sort of some of the energy consumed on the planet. You can see on a meaningful scale, till about 150 years ago, we were 100% renewable energy throughout all of human history. And then coal arrived. You can see when coal arrives, global life expectancy, that thick black line, global life expectancy, as far as we know before the invention of agriculture, is around 30 years, maybe a little more than 30 years. No different 200 years ago than it was 20,000 years ago. And then all of a sudden, you see coal add meaningfully to the energy available to the planet, and you see global life expectancy start to grow. Then you see next up is oil. Oil kicks in, you see an inflection, and life expectancy rises more steeply. This is simply the impact of energy. There's a little bit more details on history in the book that talk about 400 years ago, coal was a meaningful energy source in the United Kingdom. And where did people first start to get wealthy and first seeds of human liberty in places where energy, additional energy arrived. The Dutch Golden Age 400 years ago was the arrival of peat, basically immature coal. They dug up and burned it, but it transformed their available energy, made the Dutch 400 years ago per capita the wealthiest country on earth. That's energy. And then you can see it, natural gas in green lying on, and then you can see on top of that multiple colors, which I call the hydrocarbon derivative energy sources. Because of hydrocarbons, we can make large-scale hydroelectric dams or nuclear power plants or wind or solar or even modern biofuels. With much higher agricultural productivity, we can grow a ton of soybeans and corn in this country and make fuel out of that. Look at the rise in life expectancy in the 20th century. You can see the little swale down in World War I. This is global life expectancy. You can see a knife cut down in global life expectancy for World War II. There's another observable decline in global life expectancy in the 20th century, in the late 1950s. Free breakfast for anyone that can tell me what drove that. 2 world wars, one other decline in global life expectancy. That's Mao Zedong in China. They took away human liberty and told farmers, you can't farm your land the way you've always done. We're going to collectivize your land, and you're going to farm this way. 80 million people died in a famine, the biggest famine ever in the planet. One country deprives human liberty, and global life expectancy drops because so many people died, including so many young people. All right, we talk about where energy comes from. What matters also is what is energy used for? So very simple pie graph. The biggest use of energy you can see by far, and I would argue the most important use of energy, is industrial uses, making things. Not just making products, but making just materials. Because without an industrial sector to make modern materials, you can't build cars or airplanes. You can't build big buildings like this. That is the base use of energy that enables all the other things. Transportation, the use of energy probably you hear talked about the most. That's about 1/4 of global energy consumption. And then everybody likes to keep their homes warm at night and cool during the day and be able to pull out your cold drinks or cook on your stove. We energize our homes, and of course, key to our lives. And then commercial. This building that we're in right now, this is commercial. I saw the Denver Nuggets win last night, a little more exciting than it should have been, but the Nuggets won last night at Ball Arena. That was a perfectly lighted, perfectly temperature controlled, doesn't matter what's going on outside. That's commercial use of energy. But we forget way too much about industrial usage of energy. Thinking of industrial uses of energy, here's the 4 most important. The greatest energy scholar of my lifetime by far is this guy Václav Smil. He's from the Czechoslovakia or Czech Republic area originally. He's been a professor in rural Canada. The guy is really a brilliant polymath. He writes a lot about energy. And he termed a great term that these are the 4 pillars of the modern world. Without cement, steel, plastics, and petrochemicals and fertilizer, that enables everything else in our planet. And one other thing I'll say is 20% of global energy is used to make just those 4 materials. 20% of global energy. I missed one point on my last slide. I showed what energy was used for. Another thing I think very poorly appreciated, 20% of global energy is delivered in the form of electricity. We talk endlessly about the electricity grid, and it is important. Screw up the electricity grid at the peril of your people, at the peril of sourcing industry there, of people living there, of low-income people having an opportunity in life. Electricity is incredibly important, but that delivers 20% of global energy, the same amount of energy as we use just to make 4 materials. So electricity is important, 1/5 of global energy. Geopolitics. So here's a plot for just the top line. This is whether you're a net exporter of energy at the high in that graph or a net importer of energy down low. You can see Russia, for decades, has been a meaningful exporter of energy, and that's grown over the last few decades for 2 reasons. Their energy production has grown a little bit, and their economy and their industrial production's plummeted. So their internal energy consumption has shrunk. A large exporter. Looking at the left side of the plot going down that light blue line, that's China. I first went to China 30 years ago. At that time, China produced a little more energy than they consumed. Largest oil field one of the largest oil fields in the world, the Daqing oil field, really floated the communist revolution. Then they were a huge exporter, huge source of foreign currency, and powered their economy. Of course, they've always been a huge coal miner. They remain so today. Then their economy started to grow in industrial, and they lifted people out of poverty. It's a great story, but more and more energy consumption, but they failed in growing their energy production meaningfully. So China went from a net neutral to today. China is by far and away the world's largest importer of oil and by far the world's largest importer of natural gas. Next up, in sort of a dark blue line, that's us. That's the United States. When I was a kid, the U.S. was a meaningful importer of energy, and then that just grew. Our economy grew, we got wealthier, we did more things, and our energy production, some sectors shrunk, some sectors grew, but we didn't grow our energy production meaningfully, and really during the 80s and 90s, it shrunk meaningfully. So we became the largest importer of oil in the world, the largest importer of natural gas in the world, and then there's a little bend in that curve, like technology happens. This is the shale revolution, absolutely transformative. In about 15 years, we went from the largest importer of natural gas in the world to today the largest exporter of natural gas in the world. And in oil, we went from by far and away the largest importer of oil. Today, we're a small net exporter of liquid hydrocarbons, oil, natural gas, liquids, whatever. So you can see that just dramatic transformation in the U.S. geopolitical situation from energy. And Europe, you can see in the bottom. For a long time, they've been a meaningful net energy importer. They've continued recently to deindustrialize and therefore shrink their local energy consumption, but they've managed to shrink their local energy production even faster to remain just entirely dependent on the outside world to supply their energy. Let's zoom into one country, the United States. So here's a plot that shows both where energy comes from and what it's used for. So oil and natural gas are those 2 bars at the top. And one thing you can see right away is, wow, our country, we run on oil and natural gas. And a few other things all in single digits. 70% of the energy we consume in the United States, independent of production, 70% of the energy we consume in the United States is oil and natural gas. And they're used for a lot of different things. I'll zoom in. Oil, of course, is dominantly, but not entirely used for transportation fuels. But look at that natural gas bar. That mustard, first piece on that bar, that's for electricity production. That's just one piece of what we use natural gas for. Natural gas supplied 43% of U.S. electricity last year. By far the largest source, 2x more than number 2. Biggest source of electricity, that's just one thing we use gas for. Next up is transportation. We use a non-trivial amount of natural gas to power buses all over this country. Next up, heating and cooking. Again, I'm pro keeping my house warm when it's cold in the wintertime, and I'm pro food. Every day I am pro food. The next one, red, that's industrial heat. It takes heat, a lot of heat, to make petrochemicals, to make steel, to make cement. Like, this is a thing. The United States, for 100 years, we've been the industrial powerhouse of the world. Now, energy-intensive manufacturing, which is just one sector, but energy-intensive manufacturing, which is making these materials, including polysilicon for solar panels, that's a very energy-intensive process. Today, we use 25 exajoules total for industrial usage of energy. China uses 70. We've had a mass exodus of energy-intensive manufacturing from the United States and even more so from Europe. Wealthy countries have said, we're not going to do that here anymore. They didn't stop consuming any of those materials. They just shifted all of that over, dominantly to Asia. Most of all China, but Indonesia and a bunch of other countries. That's where you don't get rid of emissions when you shut down a natural gas-powered factory in the United States. You just move it to a coal-powered factory in Vietnam or China. When you have these jurisdictional, our state, our country is going to reduce greenhouse gas emissions, they're totally perverse. You just move the emissions, increase the emissions somewhere else. Third biggest source of energy, coal. Coal is still our second biggest generator of electricity. You can see nuclear. We use a little bit of coal for industrial fuel to make steel in this country. Wood and waste is our fifth biggest energy source. You hear a lot of promoters of wood power these days. This is pulp mills and waste stuff that we burn for industrial heat. Below wood is wind. Below that's hydro, below that's solar. So a lot of money, a lot of time, not a lot of energy. And as you can see, for those smaller energy sources, almost all of them go into one sector, the electricity sector. All right, stepping back globally, oil demand. Different countries, as we can all imagine, consume different amounts of oil. Key factor here is there's a wealthy 1 billion people. Another friend of mine, Arjun Murthy, termed the lucky 1 billion. It's spot on. The lucky 1 billion consume about 13 barrels of oil per person per year. The other 7 billion people on the planet consume on average 3 barrels of oil per person per year. What do you think those 7 billion people want? They want this. They want what you have. And honestly, they're going to get it. And they should get it. And I'm cheering for them to get it. But for that 7 billion to just get halfway to the lifestyle we have, to get just halfway to our 13 barrels of oil per day, we would need to double global oil production. Double. So when I hear these, my whole life I've heard predictions of peak oil is 10 years away for like my entire life, you know, and it is now. To me, it's just based on what? Based on immorality or bad wishes for the rest of the people on the planet, or naive beliefs we can just turn off oil if we throw some soup on a painting? Like, that's just not how the world, it's just not how the world works. All right, energy transition, following up on that. We hear this term all the time, and in fact, I think our industry, the oil and gas industry, irresponsibly uses this term all the time. Oh, our energy transition plan, we put some wind turbines up, we're doing our energy transition plan. It is important, I think, in all subjects that matter for human lives to be honest. Be honest. Don't try to be political, don't try to make people like you. Be honest. So we took a careful look at where energy growth is coming from. In 2010, the world consumed about 500 exajoules of energy. Exajoules is the technical name for boatload of joules. Now, the world consumes about 600 exajoules of energy. So where did that 100 extra exajoules come from? And by projections, we need maybe 800 exajoules by 2050. So where did that last 100 growth in energy come from? And as you can see, by far and away, the fastest growing energy source in the world is natural gas. 40% of the additional energy in the planet came from natural gas. Second fastest growing energy source on the planet over the last 12 years, oil. 24% of the additional energy came from oil. And third fastest growing source of energy on the planet is coal. Like, do you hear this in the media all the time? You know, maybe not. Fourth fastest growing, wind. 9% of the additional energy. Solar, 7%. Hydro at 4%. And sadly, as I look at that plot, nuclear, net zero. The wealthy countries, we shut down a bunch of power plants after Fukushima in 2011. Germany, Japan, and other countries have reduced their nuclear power output, I think, sadly. But India and China are growing their nuclear power output, so the net balance is zero. Nuclear produces about the same amount of energy today, in fact, as it did 20-some years ago. Nuclear was 6% of total global primary energy 20-plus years ago. Today, it's 4%. Like, this is a dense, It works whether the sun's shining or the wind is blowing. We can produce it on a small amount of land. We have an enormous resource. I really want to see nuclear get going again, because to get to 800 exajoules, we're going to need something besides hydrocarbons. But over the last 12 years, the role of oil and gas, their percent of global energy actually grew. Not only their absolute volumes grow, their market share grew, not just in this country, globally. And hydrocarbons, a tiny decline. It shrunk from like 82% of global energy to 81.2% of global energy. I don't call that an energy transition. An energy transition means a new energy source is providing more than just the growth in energy demand, and it's starting to eat into where energy has traditionally come from. That's just not even in sight. And again, I don't say that in a celebration. I went to college to work on nuclear energy. I worked on solar energy in graduate school. I worked on geothermal energy for years, 30 years ago. And I'm again working in geothermal energy and in nuclear. Liberty owns part of a small modular reactor company. We are for all energy that makes the global energy system better and makes people's lives better. So switching from consumption in the globe to US. So this is just growth in US energy production. This slide really is an illustration of the shale revolution. You could see US coal production's shrunk a lot, not because we're running out of coal, but because natural gas has outcompeted it in the electricity sector on cost and cleanliness, just lower pollutants, cleaner air if you live near also lower greenhouse gas emissions, but I think that's a distant third in its advantages over coal. Cost and just reduction in air pollution. So huge surge in US oil production, huge surge in US natural gas production. If you squint and look over at the right, you can see the growth in US wind production and US solar production. And sadly, as well here in the US, no net growth in our nuclear production. No meaningful shrinkage, but we're not growing that source. We need more energy. All right, so if we're going to get more energy in the next 25 years to get to that 800 exajoules to empower everyone, where might that come from? So here's a look at new energies. When a new energy technology started to get scale, how did it grow? So the first one to look at is nuclear power. Around the 1970s, we started to build meaningful amount of nuclear power plants in the United States. It grew, and with the scales, you can't see it so well, but we got to 2+ exajoules of energy from nuclear, and it's basically plateaued. So it arrived on the scene. We built about 100 nuclear power plants, and then they plateaued. By the late 80s, we just stopped building nuclear power plants. Political reasons, environmental concerns, I think misplaced concerns, but we got to address people's concerns. Wind and solar in the United States, that's still going on, that's still growing. So its trajectory is still going upward, but the total energy is low. Here's global nuclear, similar story to US nuclear. Grew, the plateau starts a little bit later, but sort of a flattening out in the amount of energy. You can see there at about 10 exajoules. Here's global wind and solar production. It's still growing rapidly. It depends how you count it, somewhere between $4 and $10 trillion of investment, all of it incentivized by meaningful subsidies or mandates, has driven this growth in wind and solar. But look at that total number there, 12 exajoules. A lot of math nerds in the room. I know my mom's thinking right away, 12 on 600, that's 2%. 2% of global energy today comes from wind and solar. Trillions of dollars, 2%. Now people think, wait a minute, I read all the time that it's 4% or 5%, 4 or 5%. That's the number. That's the number you'll find in the EIA data. There's one difference between the EIA number and this number. This one's right, and their number's wrong. And the reason is simple. The EIA does a very simple thing. They take the energy produced from wind and solar, the actual energy produced as plotted here, and then they multiply it by 2.5. That is a great way to turn 2% into 5%, but it's disingenuous. And the argument is, oh, well, there's thermal inefficiencies when you burn coal or natural gas to produce electricity, so you lose some energy along the way. 100% true. Often that thermal energy can be used for other sources, for heating and for district heating or industrial heating. Also, what's the movement today? We got to heat our homes with electricity. We got to cook with electricity at home. That's energy is energy. You don't get a 2.5 multiplier when your stove heats up. You get the energy produced. So to us, the only way to look at stuff is honestly and straightforward. I explain in the book why we report the actual energy and we don't use the 2.5 multiplier. Funny enough, a few weeks ago, the EIA released a note that they're rethinking this multiplier, and they may report the honest number. So here's another new energy that's came along. Wind and solar in those plots start from the year 2000. This is the shale revolution, also starting from the year 2000. And you can see that first 6 or 7 years, a lot of excitement, a lot of technology, but not moving the needle on large-scale energy yet. And then you see that incredible rise. You see the plateau, and that's when OPEC fought shale and shale won in 15 and 16. You see the COVID plateau or slight dip there, and then you see shale going forward. So that's just a whole different scale for the amount of energy that came with no subsidies, just market forces, businesses competing, a lot of businesses failing. That's important. Businesses failing is as important as businesses succeeding. That's how a competitive marketplace drives progress, drives improvement, rewards winners or ideas that work. The shale revolution today, this is 2022 data, 58% of US energy. Today, last year's data, well over 60% of all the energy produced in the United States comes from shale. And over 10% of total global energy production comes from shale just in the United States. Maybe next report I should add Canada in there. So what has it meant for the US? Here's our just energy trade balance. We imported $400 billion a year net energy. Now we're over $100 billion a year net energy exporter for the United States. To me, the biggest benefit of the shale revolution by far, lower oil prices, lower natural gas prices, lower natural gas liquid prices, not just in the US, but globally. If you make energy cheaper, more affordable, you better everyone's lives. Most impactfully, low-income people. What about air pollution? There's a lot of noise, a lot of arguments in Colorado about energy and our impacts. You know, does the production of oil and gas have negative environmental impacts? Absolutely. Everything does. If you build something, there's noise, there's dust, there's movement of materials and transformation of land. Everything does that. And we're no different. What's great about the shale revolution is high energy density. We're using less and less land to produce more and more oil and gas. And as you can see, most importantly, the most important environmental impact to me for sure is air pollution. That's what impacts humans today. About 10 million people, I'll come back to this over die of air pollution, indoor and outdoor, 10 million people. In the US, as our economies exploded in size, we've had over 80% drop in per capita emissions of the 6 criteria pollutants from the EPA. These are the things that hurt humans. We've grown our energy, grown our economy, and made our air cleaner. Now here's where I think people get confused about the energy transition. This graph's complicated. Look at the lines first. Look at the green line at the top. That's the amount of money we spend globally on developing new oil and gas resources, drilling wells and trying to keep production flat or growing it. So it peaked, $1.3 trillion globally, and then it's declined dramatically. Today globally it's less than $1 trillion, $850 billion globally for oil and natural gas production. Of course, we're spending less and getting more. We're at record high production. And then look at the yellow line. That's spending on low carbon. I won't call anything zero carbon because that's a lie. There is no zero carbon energy sources, but lower carbon energy sources. That capital, $700 billion a decade ago, over $1 trillion today of expenditures, and it's well ahead of the expenditures on oil and gas. So if you want to capture investment flows, we have had a transition. We have more spending now every year on low carbon energy sources. But look at the bottom. The yellow bar is how much energy we get from low carbon energy sources. So just an enormous amount of money. And can anyone notice a trend in the yellow bar? It's flat. So if you spend a lot of money, that's a transition of expenditures. But to date, it's not any meaningful transition of where energy comes from. And why? There's a few reasons. On the left is the energy density. With 1 acre of land, how many homes can you power with different energy technologies? And you can see with oil and gas, with an acre, you can produce enough energy to power about 180 homes. With solar power, maybe a little more than 1, because that's all the energy, not just the electricity. That's all the energy for that home. And for wind, it's a fraction of a home. So the punchline there is the energy density of oil and gas and nuclear is about 100 times higher than solar and 1,000 times higher than wind. So if it takes a lot of land, that's going to be trouble. Land use problems and conflicts, which exist in oil and gas, they exist even more in wind. Because if you need a lot of land, you're going to have a lot of conflict. And then on the right is materials. And think of this as like energy input to build the machines that are going to harvest energy. So roughly sort of 10 to 20 times more energy intensive inputs you need for cement, steel, exotic metals, polysilicon. It takes a lot of materials to harvest energy versus in wind and solar in more diffuse energy sources. They take more land, they take more materials. Maybe the biggest problem, the third one I'd say, is intermittency. I took an Uber to come down here today, and think how much you would pay for an Uber if you didn't know when it was going to show up and you didn't know where it was going to drop you off. Like that wouldn't be a high value Uber. And I wouldn't compare that Uber to the other Uber. But we have an electricity marketplace that treats these energy sources as either equal or in fact prefers the we don't know when it's going to come and we don't know when it's going to leave. The problem of that is you can build a lot of wind and solar, and then at night the sun's not shining, and then sometimes the wind doesn't blow, and you have no energy. So to keep society running, you have to have a whole separate energy system of dispatchable reliable. That's what they've done in the United Kingdom and Germany. We'll come back to that. It's just very expensive to maintain two grids, with one's turning up and down all the time as the other one is doing what the weather does. All right, health and hydrocarbons. This is quick. So globally, about 40 million people die prematurely every year because of lifestyle choices, obesity being the biggest one. Things that people do that you can impact the quality of your health, but heck, we all do the things that are fun in life. I mean, everything's trade-offs. About 40 million die from things we could change if we invested enough effort in. About 10 million die from air pollution, outdoor and indoor. So this is looking at just that environmental impacts. And there's more than air pollution, but it's dominantly air pollution. So that yellow dot is what is your risk? How many people per 100,000 annually die from these environmental factors? And as you can see in Africa and India, that's a lot. That's 250 out of 100,000 people die every year from dirty indoor air, dirty outdoor air. The planet as a whole is only about half that, half rate averaged across the whole planet. And in the United States, we're about 1/10 that, 10 times safer, 10 times lower risk from environmental health impacts in the US than in poorer countries, and 5 times better than the globe. And the reason really is the energy system. Look, there's 4 things that are meaningful in energy systems. There's wood, biomass, that's black. There's coal in gray, oil in blue, natural gas in green. If you live in an energy system dominated by wood, very unhealthy. Coal, a little bit better, not a lot in a poor country because they don't use pollution controls. And then if you go to the United States, in an energy system dominated by oil and natural gas, just much cleaner air, much healthier environment to live in. We hear the opposite, of course, all the time. Here's the same data for all the countries in the world. On the x-axis, how much oil, this is just oil, how much oil consumption per person per year. So countries on the way out there on the right are those wealthy countries consuming a lot of oil. The x-axis is the amount of people dying from environmental health impacts. So pretty clear correlation. More oil and natural gas in your energy system, safer, longer lives. All right, climate change is the long-term issue that people talk about. Well, okay, it's cleaner air, it does all those things, but what about the long term? It's a very serious and real question. I'm going to quickly run through some data on climate change. Here's atmospheric CO2 concentrations, gone up about 50% from pre-industrial times, dominantly from burning oil, natural gas, and coal. Not entirely, but dominantly, that's the big factor. I always try to put plots in context. You got to plot the whole data set from the start to the end. If you cherry pick, you can tell any story you want, and then you should try to put context in plots. So what I show there is the dotted line at the top. That's when we'll get to a doubling of pre-industrial levels. At the current rate of economic activity and energy system we've got, we're probably going to hit that late this century. 2070, 2080, something like that. I would say we're going to double pre-industrial levels of CO2. And the model sensitivity and a lot of the technical work is done based on a doubling of this forcing. We'll come back to that. The other thing I show is photosynthesis ceases. Historically, in geological time, the world in general has been much warmer than it is today and far more CO2 in the atmosphere, and therefore far more abundant life. The time of the dinosaurs, when oil and gas was created, the world was massively warmer, massively more CO2 in the atmosphere, massively more biologic and life matter on the Earth. Fortunately, a lot of that got buried and sealed in rocks, and that's our stored 100 million years of stored solar energy in the form of hydrocarbons. But if instead of raising CO2 concentration by 50%, we'd cut it by 50%, that would be a crisis. If photosynthesis stops, we drop below a threshold there. I'd even call that a climate crisis. That would be the end. Of course, we're humans, we're ingenious, we'd figure something out and we'd inject more CO2 into the atmosphere if we were going that direction. If you're from Mars and you just flew over Earth every once in a while, I think the only visible impact from a distance you would see of climate change is that the Earth is getting meaningfully greener. This is just satellite data published by all sorts of authors. There's a bunch of papers on this. They never make it into the broader press. But why is the Earth getting greener? 50% more plant food in the atmosphere, a little bit warmer, and a little bit warmer also means a little bit wetter, just better for growth of life. Doesn't mean it's better for balance for humans, but it does mean more biologic matter. This is increase in the leaf area index. Temperature, planet is indeed warming. It's been warming for about 150 years, so part of the warming predates the rise of CO2 in the atmosphere. But I, for one, am a believer that increased CO2 in the atmosphere is absolutely contributing to that warming. We can do the atmospheric physics. It absorbs infrared radiation. It makes it harder for the Earth to shed heat, and it's driving up the temperature of the planet. The warming rate from this satellite data set is about 0.14 degrees C per decade. There's another satellite data set that does things differently, and they get a little bit higher rate. So in the report and talking, I averaged the two of them and say the planet is warming, to the best of our knowledge, about 0.17 degrees centigrade per decade. We warmed a little less than 1 degree C in the 20th century. At this rate, maybe we'll warm a little bit less than 2 degrees C in the 21st century. Now, 20th century was pretty good progress. Like, no one even really noticed or talked about the fact that we warmed a little less than 1 degree C in the 20th century. Without politics, we might not have a lot of notice of the slightly higher warming rate today. Sea level rise is sort of the same story. This is the satellite sea level data. There's more tide gauge data with longer data sets in the book. But the sea levels are rising today a little bit more than 1 inch per decade. And in the 20th century, they rose a little bit less than 1 inch per decade. About 9 inches of sea level rise in the 20th century. We might get, at this rate, you'd get 13 inches of sea level rise in the 21st century. But this is the data we have. I don't know the future. But on both the temperature data and the sea level data, it's been a linear trend over the 40 or 50 years we've had good data. So we're not seeing evidence of a rising and steepening, but we don't know the future. Polar bears, you got to put some cute pictures in there, and man, polar bears are awesome. But polar bear population has more than doubled since I was a kid, and it's for a simple reason. We just have prevented the hunting and killing of polar bears. But the polar bears lived through the Eemian warming, which was the warming before the last glaciation, like 120,000 years ago. The Eemian warming was meaningfully warmer than it is today. We did not have any year-round Arctic ice at that time. So the polar bears have been around about 600,000 years. So I think their futures, as long as we don't screw up their habitat, I think their future's pretty good. Global tropical cyclones. So in the US, we call them hurricanes. In the Indian Ocean, they call them Pacific Ocean, they call them typhoons, but they're all cyclones. So this is global data that's pretty good. This is by weight, is only about 50-some years, 55 years of data. But if I put a linear fit through that, flat. Continental in the US, we have data back to 1900 of hurricanes that actually hit landfall in the US. If you put a line through that, it's actually slightly declining, but I would round it to flat. Strong and violent tornadoes, F3 plus in the US. These are actually on a downward trend. The only extreme weather event that has some trend to it. I have a theory about that. It's probably wrong. But tornadoes are still real and scary and dangerous, but they're actually on a little bit of a downward trend. Global area in severe meteorological drought. This has been gradually declining for the last 100 years, I think for a clear reason. As the planet gets a little bit warmer, remember a little more than 1 degree C warming, you evaporate more water and therefore you get more rainfall. A warmer planet means a wetter planet. A colder planet means a drier planet. Flood damage as a percent of GDP in the United States. This is 80 plus years of data, meaningful downward trend. And this is just wealth, right? Rainfall is actually increasing. Extreme rainfall events are actually increasing. So maybe the challenges of handling floods has gone up a little bit, but we're a wealthier country and we got dams and we build flood control. And so we've done a good job of that. Here's one I added, wasn't in before, but we hear the media, billion-dollar storms, the surge of billion-dollar storms. Never seen so many billion-dollar storms. Well, the world's getting wealthier and there's inflation. So if the weather is the same, of course you're going to get more billion-dollar storms. So the way to look at this is, as we have more infrastructure, more wealth, more humans, what's global damage from extreme weather measured as a percent of the size of the economy? So this pretty good data for only, say, 30 to 35 years, downward trend, dropped about 20% over the last 30 years. Wildfires, a little bit more complicated story here. Look back in the 30s, and I wish we had data further back. There's proxy data from further back. But what's clear is wildfires used to be massively larger than today. The West is a dry area, and a natural part of the ecosystem is huge fires. There was a fire called the Big Burn in Montana in 1910. I think something like 80 people were killed in a few days, firefighters, burned millions of acres in a few days. This rocked the emerging U.S. that was settling the West and all that, and they said, we're gonna stop that. We're gonna take care of wildfires. And they did. You know, we developed better forest management, thin the forest, make fire breaks in forests, thin them out, and as soon as they start, put them out. We put fire towers around everywhere. Smokey the Bear said everyone's got to participate in this. And look at that plummet. You know, from the mid-1930s to 1970s, just a dramatic drop in the acres burned. Then we got, again, well-intentioned. We care about our environment. We don't want to impact it as much, but we ended up stopping. We were logging in forests and doing things to try to control forests. And then by the 70s and 80s, that became very hard to do. And we sort of stopped forest management. No, you can't cut those trees. No, you got to leave it alone. We want a natural forest. Well, a forest that isn't burnt clean by fires is not a natural forest. So what we have today is a huge amount of undergrowth in forests. Just in the last 30 years, the amount of fuel per acre in western forests has grown by 30%. So forests today look very different than they would have looked 100 years ago, and it's because of a human impact. We controlled all the fires, and then we stopped anyone from touching them, and we stopped the fires from burning them. We've grown the fuel load in fires, and western fires are indeed on a rise, as was predicted 20 or 30 years ago based on our policies. We're starting to get political consensus to go manage fires again and bring this risk back down. I believe that'll happen, but it took us decades to get in this situation we're in today. It will be decades to get out of it. Maybe the biggest thing of all from extreme weather, deaths. How many people die from extreme weather? And I show this data because one of the most disturbing data points for me about climate change is about 20% of kids self-report nightmares about climate change. You see surveys at colleges, people are going to have less kids because they don't want to bring kids into this world getting worse based on climate change. We are impacting people's psyche, and I think making people fearful and less optimistic is never a good policy, particularly when it's not true. Here's the deaths from extreme weather. So 100 years ago, around 500,000 people globally died every year from extreme weather. Floods and hurricanes, the biggest cause of this, and droughts. Like, this is awful. Last year, this number is like 11,000. The running average over the last decade is like 30 to 40,000. So we've had over a 90% drop in the amount of people dying every year from extreme weather, and the population's grown fourfold over that same time. So your risk of dying from extreme weather is 95 to 98% lower today than it was 100 years ago. But yet we have kids more fearful than ever about climate change. All right, get into even the more nerdier stuff, economic damage. So people do analysis. There's a whole field of climate change that's climate economics. What are the impacts going to be of future warming? You know, we're going to spend money to avert climate change or reduce emissions today because we're going to avert damages in the future. Totally rational, totally logical. We had an economist, William Nordhaus, a Yale professor, win the Nobel Prize for climate economics in 2018. Nordhaus's work showed that the majority of the things we have to reduce greenhouse gas emissions, they cost far more than the damages they'd offset. His sort of optimal treatment scenario, even in a regime of much faster warming, was just do the stuff that makes economic sense. And his thing, emissions abatement, was maybe a 20% reduction that it would have been on the normal. It wasn't a zero, and certainly by 2050. It wasn't any of that. It was sort of a rational thing. Look at, all the dots are all the different studies, but look at just the center of those lines. The world's warmed a little more than 1 degree C. We'll get to 2 degrees C sometime late this century. If you look at 2 degrees C, the range of impacts is somewhere from like a positive 0.2% to a negative 2%. So if 2 generations from now, instead of being 380% richer, our great-great-grandchildren than we are, you know, they're 372% richer, is that a crisis? Is that something we would take action for today where we spend $100 on thing X and we expect a nickel's worth of benefit, or $100 for $5 of benefit? Like, these are, to me, that's not like noble, that's impoverishing. You know, we should make investments when they make sense, when the benefits, or at least commensurate with the costs. But that's not what happens in climate policy today, unfortunately. Here's another big compilation study of a bunch of economists' work. What are the big things, and I'll come back to this, that threaten people's lives today? Malnutrition, air pollution, lack of basic education, and just basic, simple health care. These things are big. Climate change is drawn on the bottom. I won't even go into the units of this. But no one who seriously looks at climate change or other global problems, no one, you know, puts it in the top 5 problems of the planet. You know, but how often do we hear about we've got to get our food supply better. We've got to make sure we increase our better health care, better nutrition, trade policy. We hear some about them, but they're like, oh, those are those other issues. They're not existential like climate change. That's unfortunate. 2 quick case studies. So Germany has spent the most per capita on addressing the climate change. Somewhere between $500 billion and $1 trillion, depending upon how you count it, in an economy less than 1/8 the size of ours. That's like us spending $5 to $10 trillion. And what did they do? Before Russia invaded Ukraine, they had tripled their electricity prices. Tripled their electricity. Today they're like 5-fold up from what they were beforehand. And what that means is, for low-income people, they heat their homes to lower temperatures because they can't afford it. Economic, industrial activity that counts on energy costs, it just left. In Germany, they do a weird thing. They subsidize industrial consumers because they don't want those plants to close, and they make consumers pay a much higher bill. The United Kingdom treats that differently. But in case Germany spent a lot of money to do something, they've slowed their economic growth. Their car production has started to decline. They were a huge chemical and steel powerhouse. Haven't built any new plants, big plants in 20 years in Germany, this industrial powerhouse nation. And they changed their energy system from 80% of their energy from hydrocarbons all the way down to 74%. Like, that's their energy transition. A lot of costs, not a lot of benefits. United Kingdom is proud. They're the biggest percent reducer of greenhouse gas emissions of any nation on Earth. They've reduced their greenhouse gas emissions by 40%. And believe me, if you talk to the energy and climate people, they'll tell you that. What they don't tell you is their total energy consumption has declined by 28%. So over 3/4 of their emissions reduction comes from one source, less energy consumption. That comes from 2 factors. One is something that used to be built, energy-intensive manufacturing, from a natural gas-powered plant in the Midlands of England, is now shut down and is now built at a coal-powered plant in China or Vietnam or Indonesia or somewhere else. That's not a climate policy, right? You get more greenhouse gas emissions, more air pollutants from burning coal than you burn from natural gas. They just moved it out of their country. Those blue-collar jobs went with them. And the other reduction in greenhouse gas, the other thing that drives a reduction in energy prices is if you make energy really expensive, guess what? People will buy less. If movie tickets were $100, like a lot less people would go to the movies. The downside of this one, so they have two dominant mechanisms for reducing greenhouse gas: export industry and impoverished people. So last winter, they had an extra spike in heating costs. Russia invaded Ukraine in early 22. So the winter of 2022, 2023, heating prices were very high in Europe. There was a huge run on firewood and wood-burning stoves and all that. Fortunately, it was a warm winter. And everyone said, oh, God, we dodged a bullet. It was a really warm winter last year. It wasn't much impact in Europe. Oh, my gosh, 10 to 20% decline in industrial production. That's a big impact. And by their own public health data, 68,000 excess deaths last winter. Think of that, 68,000. That's more people that died in the Russia-Ukraine war, far more during that winter of fighting, died in their homes in the European Union. And the reason, every year, far more people die in the winter than the summer. Globally, about 4 million people every year die from the cold. About 500,000 die from the heat. 8 times more cold deaths than warm deaths. So we always have higher mortality rates in winters. Factoring that in, the previous winters before, the average death rate in Europe, they had 68,000 more deaths than the previous winters in a warmer than normal winter. The reason that happened is low income, people in poor health, for cost reasons, they heat their homes to 62 degrees instead of to 68 degrees, instead of 70 degrees. If you're old, you're in poor health, your circulation gets reduced. When you reduce that temperature, it kills people. You make energy expensive, you make heating fuel more expensive. One thing you should think of is not just economics, you kill people. I put this slide in for kids and ask them, like, who wants to live north in Korea versus South Korea? I haven't got a lot of votes for the north yet. This is a national border you can see during the day. That's Dominican Republic on the right, Haiti on the left. The biggest source of energy in both countries by far and away is oil, because oil is the most mobile fuel. It's harder to get natural gas to a place like this. It's easy to move oil in. But Haiti's poor enough that they still have a meaningful percent of their population that get energy like all of our ancestors did, which is from burning wood. So you get deforestation. In Africa, deforestation is a huge problem. Not for clearing it to grow soybean oil to sell ethanol to somewhere. It's for heating and cooking. Haiti, Dominican Republic. This one I won't even hit, but lives are better. Human Development Index is years of education, life expectancy, and wealth. The more energy consumption you get per capita, the higher Human Development Index you get. There is no low energized rich country or highly energized poor country. They don't exist. People live very, this is from Hans Rosling's awesome book, Factfulness. He breaks down the different ways people live. This is sort of a longer way of my story of the lucky 1 billion there on the left. We've got another couple billion or so that have motorized transport, but that's a scooter. The majority of people today don't have personal motorized transport. They have a bicycle or their feet. 5 billion of today's 8 billion people are walking around today in clothes that were washed by hand. More than half of the planet, right? Because their family doesn't yet have the wealth or energy for a washing machine. Enormous time saver. Change in quality of life for women to have automated cleaning of clothes. Because in traditional societies and in most industrial societies, women clean the clothes. In traditional societies, almost always. Energy consumption per capita on the left. Darker colors means lower energy consumption, more in the dark. On the right is underage children at 5, which is a proxy for malnutrition. You can see where people have less energy, more malnutrition. Energy matters. All right, this is my quick list of world's biggest fixable problems. These are things that impact millions of people's lives. We have the technology, we have the ability to fix them. Malnutrition, basic health care, universal education, 2 sources of pollution, indoor air pollution, outdoor air pollution, and basic rule of law and property rights, human liberty. These things, any progress in these things can dramatically improve the human condition. To me, That's where all of our efforts are focused. And I'm going to talk right now about indoor air pollution. So this is clean cooking fuels. If you go back to the year 2000, 3 billion people, a little more than 3 billion people, had a stove that was powered by gas or electricity. And they didn't have indoor air pollution when they cooked. Half of the planet then, 3 billion people, burned wood, dung, or agricultural waste indoors to cook their food. And even in Africa, far more people die of the cold than die of the heat. You got to have heat at nighttime. We've made progress in this regards. Today, it's sad to say, only 2.2 to 2.3 billion people still don't have access to clean cooking fuels. That kills about 3 million people every year. Think about that. 3 million people every year die because they don't have a stove to turn on that doesn't fill their house with smoke and soot. They also have to spend hours a day to gather the fuel or dung that they're going to burn in their houses. Like, this to me is the biggest problem that's related to our industry that we can solve. We can accelerate progress on this tremendously. So I say my favorite hydrocarbon, and I love hydrocarbons. You've heard all that, right? They make our lives better. My favorite hydrocarbon is propane. Propane is what we take in our tanks when we go camping or backpacking or climbing. It's our mobile stove. If you live in a rural area, we have a house in Montana. It runs on propane. If you're not on the grid, you don't have a natural gas pipe running to you, you run on propane. What those 2.2 billion people that don't have clean cooking fuel, what do they want? One thing, they want propane and a stove. Over an hour a day to collect wood, to live in a smoke-filled hut, to kill 3 million people, the solution is propane and a stove. This is the eight biggest exporters of propane in the world. 15 years ago, the US was number 8. You can see that data point. See the blue bars on the left? That's how much propane we used to export. All the other countries, some have rolled up, some have rolled down on their propane exports. United States propane exports have surged. This is shale revolution. We now export more propane than the number 2 through 8 exporter combined. This opens the door to better lives. Most of this propane today, well, a little more than half of this goes to petrochemicals, to make polypropylene, to make plastics, which are also incredibly important. Maybe a little less than half of it goes to human direct usage. But we have the propane. Now we just need to get the ability for people to do it. On the left, that's burning wood, charcoal, whatever you've got. Smoke. Who's always over those fires? This is a picture that's not as dark as a normal hut, so you can actually see the people. But in a dark, smoke-filled hut, it's women and children that are over that fire, getting up before the sun rises in the morning to make sure that fire is big enough to heat food, to cook breakfast, to get ready for the day. There's a woman on the left. She can turn her stove on. She can cook. She can turn that stove off. She's got clean air. It's just life transformative. And we started just at the start of this year. We've talked about this year as the Bettering Human Lives Foundation. Liberty's going to fund it at $1 million a year. I'm going to try to get at least another $9 million a year from the rest of our industry. And then we'll go much broader. We'll go to the Gates Foundation, the Buffett's Foundation. Like, this is a massive bang for the buck needle mover. By our math, tens of dollars can transform a family from the left to the right. Longer health, more time, better chance to get an education, reading, empowerment of women and children. It's a long road from destitution to the quality of life we all live. The biggest jump up in that long road is I've got access to clean cooking fuel now. My life has changed. In Africa, we were in Africa a few years ago. In Africa, over 80% of the population does not have access to clean cooking fuel. In India, not long ago, it was 50%. Today, it's only 30%. India is rapidly spreading propane and cooking fuel and raising up the quality of living. You've seen the very high per capita economic growth rate in India. It is awesome. We need to get that going in Africa. We are supporting entrepreneurs. The way to do it is not charity. You don't give someone a can of propane. What do they do when it runs out? Right? The way to impact quality of life and things is to enable economic transformation, economic businesses. So there's a lot of entrepreneurs in Africa. They sell clean cooking fuel today. They've got canisters. They deliver them around to people. They've got all different business models to do it. But to borrow money to get more propane canisters in Africa, very hard to get a loan for a small business person. And if you can, it's 30 to 40% interest rate. Like, who could have grown your business if your cost of capital at the start was 30? None of us. And these are small entrepreneurs, without a savings. But man, they are going at it. We're going to provide essentially low or no interest loans to help these entrepreneurs scale their businesses up. They got 5,000 canisters, 5,000 families are living off what they're doing. Let's make that 10,000, then let's make it 20,000, then let's make it 50,000. There's so many different, we worked with a company here in Fort Collins, one of the pioneers of clean cooking stoves, EnviroFit, is a local Fort Collins company. Professors out at CSU and some graduates of CSU built very early clean cooking stoves. They sell them everywhere. In Ghana, you've already moved to Accra, you live in the suburbs, you're in the wage economy, you sell your yams or pigs, you make a little bit of money. You can save the time of gathering wood, and it's hard to gather wood if you live in an urban conurbation now. But for $1 a day, you can buy a bundle of charcoal. You've saved all that time, costs $1 a day. And that is the main fuel source people use. What does it cost to do the same thing with propane? $1 a day. Aren't they jumping at it? Because right now, to fill up that propane canister, it's $20 or $30. They don't have $20 or $30. They have a daily income, they can afford $1 a day. They don't have that working capital to pay $30 at the start of the month to get their propane canister filled. So we're working with EnviroFit, and we're a ways along to make a little sensor. Even in rural Kenya, they use a thing called M-Pesa, and in Ghana, it's a different thing. There's electronic money, tiny little phones. You sell your yams for 20 cents, you get paid electronically. That is an awesome innovation in Africa. So we're going to make it so you pick up your propane canister and you don't pay $20, you pay $2. And the valve now will give you 10% of the propane in that. And then with your phone, you pay $2 more and you get 2 more days of fuel. We're finding a technology that'll solve a working capital problem so people that are burning charcoal can move to burning propane. Because it's a financial thing. If you talk to people in Africa who are using traditional fuels, they're not worried about the health thing. That's down the road, right? They're worried about paying their bills today. So if it costs more, they're just not going to do it. And even charcoal, it costs the same. And you got smoke-filled, nasty place. But they got the $1, they don't have the $30. Their biggest thing is time. Charcoal is a game saver because they're not gathering wood for an hour and a half. They're not dangerously scrounging around and wondering where their kids are. They get to just pick up that $1 bundle. That's good. Takes 6 pounds of wood to make 1 pound of charcoal. So the deforestation problem in Ghana obviously has been bad for a while. It's worse today. So to me, the biggest thing by far is change the quality of lives of those families. Number 2 is we will reduce deforestation and environmental stresses as well. But please join us on this mission to better lives. Thank you all for coming today. It's late, but if anybody wants to stay around for questions, I'll take any and all questions on any topic. If you got to go make the world better and better your own lives, please go do it. But thank you all so much.